Thank you so much. Hello, everyone. My name is Saad Afzal, and I'm very excited to be here to present to you our work on towards battery-free machine learning and inference in underwater environments. This is a joint work between MIT and Imperial College London with my colleagues, Yuchen, Walid, Osvi, Fan, David, Fadl, and Hamid. So over the past few years, we have been on a mission to take the Internet of Things underwater. And you might be wondering why. Well, according to the National Oceanic Atmospheric Administration, more than 95% of the ocean still remains unobserved and unexplored. This means that we know more about the far side of the moon and the surface of Mars than we know about the ocean. So we've been very interested in deploying the Internet of Things underwater because it will enable many new applications. For example, one of the key applications is that it will allow us to do climate change monitoring. So today, the way people do climate change monitoring is that they have these climate models. However, they're not very accurate because people lack subsea measurements. Even though, and you need these subsea measurements because the oceans actually play a key role in the global climate system. So if you have an ocean IET, what you can do is that you could get temperature or pressure data, and then you could combine this data to create more accurate climate models. Similarly, researchers have found out that 9 out of 10 marine organisms are still undiscovered. So you could imagine using ocean IET for marine discovery to discover new marine species. So for example, you could have an ocean IET that can capture images or can record animal sounds, and then you can use this data to know about, discover new marine species and also know more about the species that you have already discovered. And then finally, you could have ocean IET for aquaculture. So according to the United Nations Food and Agriculture Organization, aquaculture is the fastest growing food sector. So an ocean IET can help you in food security. So for example, you could use ocean IET in aqua farms or seafood farming, where it can act as early warning detection systems and can help you prevent hazards such as algae blooms to optimize growth. And then this has many other applications in robotics, in weather prediction, mining, disaster response, and so on. However, despite all of these applications, what's surprising is that less than 1 in a million of IoT is underwater, even though the oceans cover more than 70% of the planet. So how do people do underwater sensing today, and why is it insufficient? Well, the vast majority of people, what they do is that they have these research vessels that they deploy in the ocean and that has a sensor connected to it, so that can collect data and then you can do some processing. However, the issue with this approach is that it is very expensive to have these research vessels and to get data from them, because it costs around $50,000 to $80,000 to have these research vessels and go in the middle of the ocean to collect data. Then another approach that researchers use is that they use these robots. So instead of having a sensor connected to a ship, now you have the sensor connected to a robot, and then the robot can roam the ocean, collect data at different locations, and then come back to you, and then you can do the processing at a remote location. However, the issue with this approach is that since the robot can only be at a specific location at a given time, this approach has very low spatial temporal accuracy. And then what recently researchers have started to use is that they have started to use something called ocean floats. Now, the interesting thing about ocean floats is that you can actually deploy them over a wide area, and they can actually get different data at different locations at the same time. However, the issue is that since they're deployed at the surface, you cannot get measurements from the deep parts of the ocean. So they can only get you measurements from close to the surface. So given that we have all of these ways of sensing the ocean, ideally what we want is we want something that is low cost, has highest spatial temporal accuracy, and then it can also explore the deeper parts of the ocean. So what we envision is a network of self-sustaining underwater sensors. So imagine that you have this sensor, but now instead of just having one sensor, you have hundreds and billions of these sensors deployed all over the globe. And this is not to scale, but you can see that how you can see the vision that you have all of these small sensors deployed all across the globe, and then they're collecting data. So for example, some of them could have temperature sensors connected to them, which can get temperature data, while others have camera sensors, which are capturing images, while others are recording animal sounds. So you have all of these sensors, and then if I want this to be self-sustaining, what I would also envision is that they have some form of energy harvesting capability. So they can also harvest energy. So, and then when a drone comes by, what these sensors can do is that they can just offload their data to the drone and then communicate their data, and then the drone can come back to us and then share this data, and we can do some form of processing. So in summary, what we want is that we want ultra low power and self-sustaining ocean IoT sensors, which also have a capability of sensing and communication. And in fact, over the past few years, we have actually showed that you could have such sensors, and we have showed this over multiple papers that you could have these low power sensors that you could use for batteryless sensing. And then we started thinking that, can we actually use one of these sensors to enable one of the applications that I talked about? So for example, can we use these sensors to enable a bioacoustics application to detect marine animal sounds? So in this application, we want to detect marine animal sounds, and it has many applications in, for example, in aquaculture, and as I said, in marine discovery, and also in the Marine Mammal Protection Act, and so on. So you have this underwater sensor that has a hydrophone connected to it, and then let us say that a marine animal comes by, produces a sound, and the hydrophone records it, stores it to the memory, and then when a drone comes in, it just offloads the data to the drone, and the drone gets the data. However, now you might be thinking that, is this enough? Like, can we just use this as is and get data from the ocean? And the answer is that this is actually not enough, and it's not so straightforward. And the reason is because if you want these underwater sensors to be low power, you end up relying on these low cost, low power microcontrollers, which are memory constrained and compute constrained. So why is this a problem? Well, imagine that you have this memory constrained device that you are using to store the data. So there will come a point where you will run out of memory. And not only that, in underwater environments, it's actually much worse, because like most of the time there is no animal. Like most of the time you're just recording noise. And what we have seen is that if you use these low power sensors, you can actually get less than 10 seconds of audio, which is like not useful for many of the practical applications that I talked about. So what we want is that we want to somehow be able to do record this data and still be able to record it over a long period of time. So what we started, like the questions that we ask ourselves is that, how can we enable long-term sensing within the memory and compute constraints of ultra low power nodes? And we started thinking that, is there a way for us to first know if there's animal sound or if it's just underwater noise? Because if we can differentiate between the two, what we can do is that we can just store the animal sound and just discard all of the noise data that we recorded, which will make our memory consumption much more efficient. So the first question is that we ask is that, how can we determine which sounds need to be stored and which ones are the ones that can be discarded? And then the next question that we ask is that, can we take this one step further? And instead of just doing detection, can we classify between different animals that are producing the sound? So for example, if there's one marine animal that produces a sound, can you actually tell which animal produced it? Because then you can just store the identity of the animal, which consumes, let's say, 1 or 2 bytes, instead of storing the whole raw signal. And the question that we ask is that, can we use these sounds to identify animals? And then finally, what we are interested in is that, can we take this one step further and actually be able to adapt to different environments? Because in its current state, if we were to use a sensor and deploy this in different locations, this wouldn't work, because different underwater locations have different noise variations. So if you were to deploy this in different locations, you would need to do some form of adaptation in order for you to sense the data. So the third question that we ask is that, can we develop machine learning models so that they can adapt to different underwater environments? And the one thing that you will notice in all of these 3 questions is that there's a common theme, which is that you need some form of battery-free inference in order for you to deliver answers to these questions. And another thing that I want to share here is that what's interesting about all of these questions is that they apply to all of the applications that I talked about. So for example, here I just focused on the bioacoustics application, but it's the same problems when you're talking about, for example, if you're capturing image data, or if you're capturing time varying data, for example, pressure, temperature data. So in this talk, what I would do is that I would first explain the first battery-free device that can enable battery-free inference in underwater environments. Then I would go ahead and show you how we can use this for a bioacoustics application. And then finally, I will end this talk by highlighting some open problems and challenges in battery-free inference. So first of all, let me show you what the overall system architecture looks like. So here you have your underwater sensor connected to a hydrophone, and then this also has some energy harvesting capability. And then there's a microcontroller connected to it that does some onboard processing. And then I also have a communication protocol to communicate data back to the drone. So I will focus more on the onboard processing part, and then I will take a step back and tell you how all of this comes together. So recall from the 3 questions that I asked earlier that what I want to do first is that I want to know whether the sound that I recorded came from an animal or was it just noise. So let us say you have a hydrophone that records some sound and then feeds it to the microcontroller. Now, this problem is actually well known in the bioacoustics community, and they also know that you can just not, that it's not possible for you to just look at the signal and be able to tell that whether this is a sound coming from an animal or whether it's just noise. Because the thing is that underwater environments are very noisy. So you cannot just look at the signal and do some form of thresholding. So in fact, if you were to look at the 2 signals, you can see that it's very hard to tell them apart. So instead, what people do is that instead of looking at the signal in the time domain, they construct spectrograms. So in the interest of time, I wouldn't go into much detail into how these spectrograms are computed, but you can think of these spectrograms as a 2D representation of the signal in time and frequency. So for example, here, the light green regions correspond to the background noise, while the bright yellow regions correspond to animal sound. And then if I were to see the spectrogram of the 2 different signals, you can easily distinguish between the 2. So now you could have some form of inference going on these onboard microcontroller processors for them to be able to differentiate between the 2 spectrograms and tell you that if the signal is coming from just noise or is this coming from an actual animal. So actually what we can do is that like we can do detection, but we can also take it one step further and we can do classification as well, where we can actually differentiate between the different animals that are producing this sound. And we can use something very simple, such as a convolutional neural network, to achieve this. So one question that you might ask here is that, can we just use the convolutional neural network models that are available online and just use them and deploy them onto this device and do this classification? Well, it turns out that it's not very simple. And the reason is that this device is memory constrained. And it actually turns out that state-of-the-art machine learning models consume a lot of memory. So they actually consume memory in the order of megabytes, around 2 megabytes. And the memory that we have on board is more or less around 256 kilobytes. So what we want to do is that we want to somehow truncate the model or make it smaller so that we can upload it to the microcontroller and do onboard inference. So for this, we actually developed 2 different techniques. And in this talk, what I would do is that I would go over both of these techniques at a high level, but if you're interested, you can go to the paper and check out the details. So the first technique is that we resample the input signal, and the second is that we reduce the number of convolutional neural network kernels. So for the first technique, what we want to do is that we want to reduce the size of the recorded signal. So imagine that you record some sound, and right now in its current stage, it consumes around 272 kilobytes of memory, which is huge. So in its current state, you cannot even store this whole sound on your memory because it's already above the memory limit. So what you want to do is that you want to resample the signal. Now, one option is that you just drop every other sample and just store this new resampled signal on your device. However, the issue with that approach is that you cannot store, or you cannot basically store higher frequency data. So what we do is that we actually intelligently subsample the signal so that we can also maintain the spectral efficiency of the signal. Then the other technique is that we can reduce the number of convolutional neural network models. And for that, what we can do is that, for example, you have a model which has a lot of layers and convolutional layers and then dense layers. So what you can do is that you could actually see which of the layers are contributing the most to the accuracy and then drop the ones that are not really helping you in achieving a higher accuracy. So this required a fair amount of hit and trial, but what we saw that if we do this, we were able to reduce the size of the model from 100 kilobytes to all the way down to 60 kilobytes. So by using these two techniques, what we were able to show is that we could lower the overall memory consumption by around 200 times so that we could fit the overall model on our device. And not only this, if you take it one step further and do classification, then we can, and just store the inference result, then we can get 1,000 times more improvement in memory consumption. So now that I've told you how we can perform onboard inference, the next thing that I want to share is that how can we communicate this data? So here was our overall system architecture, and I want to know that how can I communicate this data from the processor back to the drone? So for this, we actually leverage our prior work on underwater backscatter. And to explain how underwater backscatter works, you can think of this sensor as a mirror. So imagine that your sensor has a switch connected to it. So when a drone comes close to it, it produces a sound. And when the switch is open, the sensor just harvests energy from it. Because it's a transducer, it converts mechanical energy to electrical energy. And then when the switch is closed, what happens is that it reflects the incoming energy back to the hydrophone. So it's almost like you're transmitting a bit 1. And then when the switch opens again, you're not transmitting, not reflecting the signal. So it's like you're transmitting a bit 0. And just by simply toggling the switch between the two states of on and off, what you can do is that you could communicate your data in binary and send bits of 1s and 0s. So in this way, you can communicate your data, and this actually closes the loop because I've told you how we can harvest energy, then how can we do onboard processing, and then how can we communicate this data. So far, what I've told you is I've just showed you one node, but this actually this is applicable for many, many different nodes. So you could have all of these different nodes doing communication and sensing the ocean at a wide scale. So now that we know how we can do all of this, the next thing that I want to talk about is how we can implement these nodes. So we fabricate our own transducers. We 3D print the caps, laser cut the washers, and then assemble this entire thing and cure it under pressure at 60 PSI for 6 to 8 hours. And then we also use our own off-the-shelf microcontroller development board, which in this case is the MSP 430FR5994. And the thing about this specific model is that it could not, the ADC on this model could not sample negative voltages. So what we did was that we added a clamping circuit, which added a DC offset to the signal and shifted it upwards so that the ADC on the MCU could sample the right signal. And we also thoroughly evaluated our system. So for example, we looked at how the model accuracy is for different cases. So the first case that we looked at was detection, where we want to just differentiate between noise and like if there's a animal sound. And the second case is where we want to classify between different animal sounds. So for the first case, we got an accuracy of around 92%. And for the second one, we got an accuracy of around 84%. And then we also evaluated the power consumption of our device, and we found that it consumes ultra low power of 3.13 milliwatts. And from prior research, we know that actually in underwater environments, you can harvest several milliwatts of power. So this shows us that you can actually operate this prototype entirely battery free. And then we also I showed that like by using resampling and trimming, you could actually reduce the convolutional neural network model by a factor of 200. And then if you go beyond that and do inference, you can reduce the memory consumption even further, and you can make it more efficient by about 1,000 times. So given that we have all of these results, these results are actually very promising, and it's very exciting to be working in this area because this tells us that having underwater inference is actually possible. You could actually do underwater inference. So there are some open problems and challenges that I would like to talk about now. But this at least shows us that we could do underwater inference with high accuracy. So the first problem that I want to talk about is that how can you adapt to different environments? So as I said earlier, if you were to deploy this sensor in different locations, this wouldn't work because they experience different variations of noise. And we actually tested this and verified this. And we saw like if we train some model, and then we perform inference on the underwater sensor, and then if we give it some different kind of noise, then the accuracy drops from 84% all the way to 63%. So we need to do some form of on-device learning in order for these nodes to adapt to different environments. So the question that we asked is that can we perform on-device learning to locally fine-tune so that it fits different data distributions? And then the next exciting problem that we are also working towards is that can we enable underwater inference for other applications? So for example, in this talk, I talked about the bioacoustics application, but can we use the same ideas that I talked about to enable other applications, for example, for climate monitoring or marine discovery? So like, can you use other sensors as well, like temperature sensors, camera, and pressure sensor to do this? And then finally, the third problem that we're interested in is that can we enable battery-free distributed machine learning on these devices? And what I mean by that is that imagine that I talked about one sensor doing this inference, but imagine that if you have a distributed network of these sensors all performing inference, and then what if they share their weights or parameters with each other so that they can better train their networks and also improve their accuracy? So is that possible? So all of this is very exciting, and I'm very interested to be a part of this research area because there's still a lot of things that can be done in this area, and there are many, many applications for it. For example, you could use this for climate monitoring, as I said, and then you can use this in ocean exploration to discover new marine species. And then not only that, you could use this in aquaculture to monitor growth and even to detect new diseases on fishes. And I actually invite you all to join me in this research work so that we can all enable more applications that weren't possible before. And we have also open sourced our code and schematics and tutorials so that if any one of you want to build these underwater battery-free sensors, then you can do that. And I would also be happy to give you one of our sensors if you are interested in this work. Thank you for listening to this talk.